In the previous lesson, we talked about converting between a logic expression, boolean expression, which was represented in what we're going to refer to as boolean algebra, converting that to a circuit diagram, a schematic, using the gate symbols, and then converting to a truth table. We did it kind of as an introduction, so probably would be a good idea to do a couple of more. Let's go ahead and try that. So I am going to come up with, let's see, some sort of a Boolean expression. All right, how about that guy? This says X, our output, the output from our circuit, is going to be the combinational logic of the inverse of A ANDed with the inverse of C, ORed with the value that's at B, ANDed with C. All right. Now, real quick refresher, we had the three primary gates that we were worried about using: the inverter, the NOT, the one that's represented with those bars over a symbol, and everything under the bar gets calculated first, then you take the inverse of it to see what the output of that inverter is. Then there was the AND gate with multiple inputs. All of those inputs have to equal a 1 before the output equals a 1. That was represented with those dots, or the product. Then there was the OR gate, and the OR gate also had multiple inputs, like the AND gate had multiple inputs, but its output was a 1 if any of the inputs were equal to a 1. And that symbol was represented with the plus sign, or the sum. So, many of you probably have experience with in mathematics with this saying PEMDAS, right? And this represented order of operations, the order in which you were supposed to do or perform operations in one of these expressions. And And it said parentheses first, then exponents, then multiplication, then division, then addition, then subtraction. Well, we don't have quite as many operations when it comes to our Boolean expressions, but there's still some. For example, we're going to do the parentheses first. Now, an interesting thing about the not is that everything under the bar is considered really to be in parentheses. So if I have an operation like A or B, and then I have a bar over both of them, really, this bar over both of them is equivalent to saying, put parentheses around that A or B, do everything under the bar like you would parentheses. Then after you do your inverses, then you do your ands, the multiplication. Then you do your ors, the addition. All right? So we're going to do a couple of these, and we're going to play around with these as if they were, well, algebraic expressions. Now, I know that algebra may not have been your favorite subject, but this is going to be really easy. Easy? Yeah, let me tell you why. In algebra, how many numbers do you have? Well, infinite, right? You have an infinite number of numbers. Even if you're sticking with integers, still have an infinite number of numbers. How many numbers do we have with Boolean expressions? 2. We have a 0, we have a 1. And that makes things easier. It makes things a little bit more straightforward. Now let's take a look at this expression up here. First of all, if this were a mathematical algebra expression, what's the very first thing you do? Well, the very first thing you do is probably the additions, right? Actually, no. The very first thing you do is the multiplications. Then you do the additions. But we do have that weird twist thrown in with these bars. So what I'm going to do first is I'm going to go ahead and draw this circuit. I'm going to start out by looking at all the variables that I need as inputs here. I have A, I have C, it appears twice, but I have C, and I have B. So I'm going to go ahead and draw over here A, B, and C. These are our input signals. These are the signals that we're going to start propagating from left to right through our logic circuit. Now, what's the very first thing you do? Well, let's take a look at this guy right here, this product right here. It says I am going to AND the inverse of A with the inverse of C. That means that I need to run A through an inverter to get A bar, and I also need to run C through an inverter in order to get C bar. So now that I have A bar and C bar available to me, now I can AND them together. So I'm going to take an AND gate. I'm going to run A bar in, and I'm also going to run C bar in. So at this point, I have A bar ANDed with C bar. All right. Now, that takes care of that. Can I OR this with B? No, because this AND has precedence over this OR, so we have to compute the B and C first, which means another AND gate. Do I have B available? Yeah, it's right there. Do I have C available? Yep, it's right there. The value that goes in before hitting that inverter, right? So I'm going to create another AND gate. And this AND gate is going to have B ANDed with C. And so I've got B and C. Now, Back in the old days, whenever we crossed two lines in one of our circuits, we would do this little hoppy thing, this little loop, to make it look like the wire was actually jumping over the other wire. That's kind of gone out of style mostly because now most of our schematics are drawn in CAD systems, and the CAD doesn't have to interpret that as a connection or not a connection. But whenever I draw these up on the board, what you're going to see is if there's a cross like that, there's no connection. If, however, I put a heavy dot right where the intersection occurs, that means there is a physical connection. So right here with just those two wires crossing over each other, there's not a connection. All right, am I done with my circuit? No, because the last operation is I have to OR this signal with this signal. And so I create an OR, and I OR the output of those two ANDs together, and here is my X output. All right? So this gives us a real good view from left to right as the signals change, how they propagate or pass through these different gates. Let's draw the truth table now. And we're going to draw the truth table in the same progression that we drew our circuit. So, first of all, let me go ahead and I actually give myself a little bit more room here. All right, so we have the three input signals, A, B, and C. So we have 0, 0, 0, and we're going to go and list every possible value. The truth table is not complete unless we have listed every possible pattern of ones and zeros at the input. So remember, three inputs, I have 2 to the 3 or 8 possible patterns of ones and zeros. 4 of them are going to start with 0. So I've already listed one of them. 4 of them are going to start with 0. 4 of them are going to start with 1. Then B, there's going to be 2 zeros, 2 ones, 2 zeros, 2 ones, and then C is going to be alternating 0, 1, 0, 1, 0, 1, 0, 1. All right? Now, let's do this exactly the same way, or in the same progression, that we did this logic circuit. What is the very first thing that we needed to do? Well, going left to right, the first thing that we needed to do was we needed to compute A bar, and we also needed to compute C bar. So let's make a column for A bar and a column for C bar. Now, the output of an inverter is just the opposite of what the input is. So for each one of these rows, for A bar, figure out what the opposite of A bar is. So for these first 4 rows, A bar is going to be a 1 because A is a 0. Where A is a 1 in these last 4 rows, A bar is going to be a 0. All right. C bar. What are we looking at here? Well, C bar is going to be the inverse of C. So everywhere C is a 0, C bar is going to be 1. Everywhere C is a 1, C bar is going to be a 0. And we get this alternating pattern 1, 0, 1, 0, 1, 0. All right. Now, what was the next thing we did? Well, the next thing we did was we figured out what the AND was, the product of A bar and C bar. So we have A bar ANDed with C bar. And by the way, later on, we're going to show, in a later lesson, we're going to show why A bar and C bar is not equal to A and C with a bar over both of them. That's a different expression. I'll show you that in a later episode. So, how does the AND work? The AND works if I have a 1 for A bar and a 1 for C bar. Where does that happen? Well, A bar is a 1 here, C bar is a 1 here, we have a 1. Go a little further down, the third row, A bar is a 1, C bar is a 1, so the output of A bar and C bar is also a 1 there. For all the other rows, there is at least 1 0 at the input, and a 0 going into an AND gate forces a 0 on the output. All right. What was the next thing that we did? Well, the next thing we did was we took a look at that B and C. So B, the product of B and C, what does that look like? Well, the inputs for B and C come back over to these original inputs, B and C, these columns right here. When are both B and C equal to 1. Well, it's not equal to 1 until you get to this fourth row. So B and C are both a 1 in the fourth row. Notice A doesn't have anything to do with this. Then we go a little bit further down and we see in the last row, B and C are both 1s in the 8th row. Once again, A doesn't have anything to do with this, but we have B is a 1, C is a 1, so B and C is a 1. All the other rows, we got zeros. All right. Now for our last column. In the last column, what we're looking at is what happens when we take A bar and C bar and OR it with B and C. What's the result? Well, these two columns represent A bar and C bar and B and C. All we need to do is OR those two columns together. And when we OR those two columns together, we get 1 or 0 is 1. Remember, a 1 at either input of an OR gate, this OR gate, a 1 at either input is going to output a 1. So we have 1 or 0 is 1. 0 or 0 is 0. Two zeros ORed together make a 0. Kind of like 0 plus 0 is 0, right? 1 or 0 is 1. 0 or 1 is 1. 0 or 0 is 0. 0 or 0 is 0. 0 or 0 is 0. And then 0 or 1 is 1. All right? So there we go. There is the truth table for this expression up here. Now, what I'd like to do is kind of say this like a sentence. We did this before whenever we first started talking about ands and ors. I could say x is equal to a 1 if A is not equal to a 1 and C is not equal to a 1, or B is equal to a 1 and C is equal to a 1. So let's go down this rows and see if that kind of makes sense. So if A is not equal to a 1 and C is not equal to a 1, well, that happens in this row, the first row, where A is a 0, B is a 0, and C is a 0. And it also happens in the third row, where A is a 0, B is a 1, C is a 0. We come over, we see, yep, there are two 1s in those rows. There are 1s in those rows. Or if B is a 1 and C is a 1, well, that happens in the fourth row, where A is a 0, B is a 1, C is a 1. Look, we got a 1 out. And then it happens in the 8th row, where A is a 1, B is a 1, C is a 1. We've got a 1. Okay? All the other cases where where either of those is not true, where either of those products is not true, we're going to be outputting a 0. Makes sense. All right. In our next lesson, we're going to be talking about a special type of gate, a special type of operation called a decoder. What it's looking for is, when is the one case when all of these things are true? Sounds like an AND gate. It is an AND gate, but it's a special kind. So we'll talk about that in the next lesson. Ben Franklin was a bright man. Guess you weren't expecting a computing or a computer organization lecture to start out with a discussion about Ben Franklin. Sounds a little bit more like a history lesson, doesn't it? Well, let me explain this, because Ben Franklin, although very bright, makes a lot of starting electrical engineers and electronic students well, it makes their life a little difficult. And the reason is because of this weird thing called, well, current, electrical current. Back in Ben Franklin's day, or earlier, there was a theory about the flow of electricity being this idea of a fluid flow. And so they already knew about something like a current flowing back and forth. And one of the things that was, one of the ideas was that it was a two-fluid theory. There was one fluid that combined with another fluid, and they retracted to each other, and the fluids flowed through conductors in order to, kind of combine with each other and null each other out. Ben Franklin believed in the one fluid theory, and this idea that it was a fluid, a higher potential. If you've got a bucket of water, water will flow downhill, and so you had this higher potential, this excess of some fluid, and it flowed to counteract a deficit of fluid in the other direction. And so he picked a direction, right? He said, okay, we're flowing from here to here, positive to negative, higher potential to lower potential. What's actually flowing? Turns out electrons are flowing. It's the excess is actually flowing uphill. And so all of the ideas, all the principles, all the computations and so forth based around electricity are discussing current flowing downhill when actually the active thing flowing is the electron flowing up. And when you look at circuits, oftentimes we have this idea of a positive being a logic 1 and a negative or an absence being a logic 0. So what's actually doing the flowing here? Well, the thing with the pressure, the thing with the active nature is the 0 that has to flow, okay? And this brings us to this idea of something called an active low circuit or output. Now, an active low output, what that means is that the active nature, the yes, the power, the one that's going to flow the quickest is going to be a logic 0. So this means that the active state is a logic 0. And the inactive, or I'm going to refer to this as the idle state, is a logic 1. All right, so we've got this idea of active and inactive. And in fact, when you think about logic 1s and logic 0s, typically you think of a 1 as being active, true, yes, right? And the 0 being the inactive or the false. And that's not always the case. Let's talk about an AND gate. In fact, let's just go ahead and do a truth table for A. Well, I don't need it on that side. Have my inputs listed on the left side, and then A and B. We'll do a quick truth table for this guy, right? Now, what does the AND gate look like? If you remember from our discussion about the property or the rule, the algorithm that drives an AND gate, you're familiar with this idea of if all the inputs are a 1, I'm going to be a 1. All right? Now, if there's a 0 at any input, I'm going to output a 0. So this is the truth table for an AND gate. Turns out that there is, well, an active low version of this guy. And in fact, what we'll do is I'm going to make another column here, and this will be A and B with a bar over the top of it. And this guy, this is going to be our active low version of the AND gate. It's going to be a 1 anytime we're outputting a 0, and it's going to be a 0 anytime we're outputting a 1. Notice the bar over the top of it. And in fact, this circuit is used so much that it's got its own name. And the name includes the word AND, thankfully, because it operates like the AND gate. What they do, though, is they say, well, it's really a knotted AND, right? Well, you say that quick enough, what do you come up with? You come up with the word NAND. So this gate right here is so common that it's actually got its own name. It's called a NAND gate. Now, think about this. What the circuit actually looks like. We've got an AND gate. And I have to be careful how I say this. Sometimes I talk a little fast, and so when I say a NAND gate, I say it really quick, and I say an AND gate, and that kind of sounds like an AND gate. Which did I say, an AND gate or an AND gate? Well, hopefully the circuits will make it clear. So this circuit right here has A and B going into an AND gate, right? And then passing through an inverter to come up with A and B bar, okay? Now, this circuit, once again, is so common that what we see oftentimes is the circuit is drawn like this. Remember, I told you whenever we were first talking about logic gates that the triangle really doesn't imply the inverter. What implies the inverter? The circle. So we just put a circle at the end of an AND gate, and we've got our NAND gate. All right? Now, that was pretty quick. There's one other thing, though, that I want to talk about. We talked in the last lesson that what an AND gate can be used for is to identify unique conditions. For example, if I've got A and B, A ANDed with B, the active row is when A is a 1 and B is a 1, right? Yes, but what if I don't want to figure out whenever A is a 1, B is a 1? Instead, I want to identify when A is a 1 and B is not a 1, okay? Turns out there's exactly one row for that too, exactly one condition when that's true. So let's go ahead and change this around a little bit. I'm going to change this row and thereby also my active low row. And instead, I want to say, I want to put a 1 when A is a 1 and B is a 0. Which, another way of saying that is A ANDed with B bar. That is going to say, as long as A is a 0, we're still going to output a 0, because this is going to be 0 ANDed with something, right? As long as B is a 1, B bar is going to be a 0. So as long as B is a 1, B bar is going to be a 0, and you'll have something ordered with ANDed with 0. The only time we're going to output a 1 is the case when A is a 1 and B is not a 1. And the active low version is going to look like that. Okay? So this circuit right here is just saying that and I need to finish up my expression there, that I want to output a 1, or I want to go active when A is a 1 and B is not a 1. All right? It's a pretty common circuit. So I can actually move this active row to whatever row I want in the AND gate just by adding or taking away bars, just inverters. Okay? Now, this circuit right here is actually pretty easy to draw too. What I'll do is I'm simply going to take my NAND gate, right? And instead of running A and B through an inverter, remember the circle makes the inverter, I'm just simply, for A and B bar, I run A straight in, and then B goes through a circle, an inverter, before coming out. And this circuit right here is A ANDed with B bar with the output inverted. All right? So, maybe we want to figure out whether we have maybe 4 inputs. And I want to figure out the condition. Maybe my 4 inputs are A, B, C, and D. And I want to figure out the unique condition. And this, by the way, is referred to as a decoder. I want to decode the unique condition when A is a 1, B is a 1, C is a 0, and D is a 0. All right? What does it look like? Turns out that the circuit is quite simple. X equals, first of all, we're looking for a condition that involves all 4 of those variables. What does A need to be? A needs to be a 1. What does B need to be? B needs to be a 1. What does C need to be? C needs to not be a 1. What does D need to be? D needs to not be a 1. Wow, that was a real quick way to create a logic expression, wasn't it? And what does our circuit look like? Well, the circuit is just an AND gate again, right? With A, B, C, and D as the inputs. A goes straight in, B goes straight in, C passes through an inverter before going into the input, and D passes through an inverter before going into the input. All right? What does our output look like? Well, it depends on whether we're looking at an active high or an active low circuit. If it's an active high circuit, we're done. We just need to put the output X there. If, however, we're looking at an active low circuit, put your inverter and then you're good to go. We've come to a dreaded lesson. Dreaded? How could this be anything but fun, right? Well, turns out that, or at least rumor has it, a lot of people don't like algebra. Well, this is going to be a little different because what I'm going to do in a future lesson is show you how there are some kind of red flags to guide us on our ability to do simplification of boolean algebraic expressions. But before we do that, what I want to do is just show you a quick example of how boolean expressions, well, you can manipulate them, move them around, change them around so that we can have two expressions that are exactly the same thing. Well, not exactly the same thing because their performance may be a little bit different, but the output, the result, going to be the same thing. So let's do one real quick. How about x is equal to a or a bar b? All right. Now, real simple expression. Just heck, how many gates do we have? Well, we have an inverter that A passes through. We have an AND gate that A and B will be passing through, and then we have an OR gate that all of them get combined for the output X. Let's do the truth table, and I'm just going to start out with a quick. We'll just do a little truth table. I mean, it's just 4 rows, right? So we have A, B, 0, 0, 0, 1, 1, 0, 1, 1. Here we go. Now, if you were to look at this as a mathematical expression, what's the first thing that you'd do? Well, first thing I do is the ands, right? So I've got to do this and, but before I can do that and, I have to actually take the inverse of B. The inverse of A. So take A. A bar, and that means that this column right here, I'm going to take everywhere that A is a 0, I'm going to flip it to a 1. Everywhere A is a 1, I'm going to flip it to a 0. All right. All right, that was pretty simple. Now I've got A bar and I've got B. This column right here is B. So now I can do the column for A bar ANDed with B. What does that look like? Well, it's going to be the AND of this B column with this A bar column. So 0 and 1, remember they both have to be a 1 to output a 1. So we have 0 and 1 is 0. 1 and 1 is 1. 0 and 0 is 0. 1 and 0 is 0. All right? So if I were to look at the output where that gate comes from, the output of that gate, this is the pattern of 1s and 0s I'd see based on the different inputs that could come into the circuit. Now, the last step is to take the or A with A bar ANDed with B. So I've got this column, A bar ANDed with B, and I'm going to OR it with the first column of A. Now remember, the OR said if any of my inputs are a 1, I'm outputting a 1. So 0 or 0, no 1's there, so that outputs a 0. 0 or 1, 1. 1 or 0, 1. 1 or 0, 1. All right. Does that look oddly familiar? Well, kind of looks like just an OR gate, doesn't it? I mean, if you look at, in fact, let's go ahead and do a column for this. A or B. All right. Now, 0 or 0, that's 0. 0 or 1, that's 1. 1 or 0, that's 1. 1 or 1, that's 1. Yeah, looks like this column is equal to this column. And we've seen right now a serious, benefit maybe is the word I'm looking for, of Boolean algebraic expressions versus mathematical algebraic expressions. To prove something is true in algebra, I don't know if you remember these things, but there were line by line by line by line by line proofs that we had to make, right? This is true. If this is true, then this is true. If this is true, then this is true. All you need for Boolean algebra is a truth table. All I need to prove that this guy just so happens to equal A or B, that's true. Why do I know? Well, I've shown you that for every possible case, it's true. Every possible case, A or A bar B is equal to A or B. What does that mean for us? Well, what that means is that I can manipulate these, just because I got an algebraic expression, Boolean algebraic expression in a certain format, doesn't mean that I can't change it, manipulate it, move it around a little bit to make something better, okay? Better. What makes it better? Well, let's do these circuits, all right? So I've got A, B. Those are my signals into this circuit. So if I'm coming left to right, going through these expressions, let's do the A or A bar B first. The very first thing we did was we computed what A bar is equal to, right? So right at this point, I've got A bar. Now, once I had A bar, I could AND it with B. So I'm ANDing it with B. So at this point in this AND gate, I've got A bar ANDed with B. And then the last step was to OR A with the output A bar and B. So I'm going to create an OR gate here. And that's going to take this value of A all the way over. There you go. This is the circuit for that expression. What's the circuit for this expression, A or B? Well, it's just an OR gate, right? Now, let's take a look at, well, the differences between these two circuits. First of all, this gate, the bottom one, the A or B, there's just one single gate. For the top one, there's 1, 2, 3 gates. Now, granted, one's an inverter, and that's going to be a pretty quick gate, but still, you've got two input gates and one input gate. So there are 1, 2, 3, 4, 5 inputs into different logic gates and 1, 2, 3 outputs for these logic gates. Pretty complex circuit. Now, we're going to talk about 3 things in particular. First of all, which circuit do you think is faster? Well, every single gate I pass through incurs a little bit of a delay. And so I've got a very small delay with this inverter, but then I've got 2 slightly more significant delays with those 2, the AND gate and the OR gate. So I really have kind of 3 stages that signals that any change in the signal, for it to propagate all the way, if A changes, it has to propagate through the inverter, the AND, and the OR gate before we can be sure that X is correct. All right. How many stages or levels of delay do we have to pass through here? Well, just one OR gate. So the bottom circuit, this one is faster. Right? Second, every gate requires power to run. It takes some energy, which usually that energy, unless it emits itself as light, it's going to emit itself as heat. It's going to burn off as heat. So which one generates more heat? Which one uses more power? Well, this one's got more gates, so this one's going to run with, this is going to require more power to operate. This one is going to require less power. So the OR gate wins again in less power. All right. All right. What about the next one? So it's faster, it's less power. And by the way, this also translates to our code. If you had done a conditional statement, an if statement that said if A is equal to 1, or if A is not equal to 1 and B is equal to 1, that would have taken more time to process than just is A a 1 or is B a 1. You know, your code is actually going to run faster too. One last thing. These guys are made up of transistors. Transistors take up space on our silicon, on the actual chip, or the circuit board. Which one is going to require more transistors? Well, since the OR gate is included in both of these circuits, but the top circuit actually adds an inverter and an AND gate, top circuit's going to take more physical space on our board. So more physical space. Oop, didn't do that quite right, did I? I know some of you are sitting back there watching me do that and screaming, "Tarnoff, you screwed that up." Let's try that again. Less physical space. And in fact, the less physical space has another very closely related item. Once again, this top one takes more transistors, bottom one takes fewer transistors. That means it also costs less. All right? And that didn't really show up on the camera, but you get the idea. So it costs less. So in every way you look at it, this bottom circuit is better than the top circuit. How did we know that the top circuit and the bottom circuit are kind of interchangeable? There's our truth table. Now that we've got our feet wet with this manipulation of Boolean expressions, let's talk about some identities of Boolean algebra. Now, you all are familiar with this idea of an identity, and you may not know the term, but I'm sure you're familiar with the fact that A times 0, or anything times 0, equals what? 0, right? Anything times 1 equals what? Itself. Anything plus 0 equals what? Itself. And so we have this idea of these identities. Well, it turns out that in Boolean algebra, they work phenomenally well. Whenever you only have the values of 0 or 1, the identities work out pretty neat. They're kind of nifty. So let's talk about our three properties, right? Or excuse me, our three logic operations. We have and, right? We have or, and then we have exclusive or. We haven't talked a lot about exclusive or whenever it comes to Boolean logic, because it turns out, or excuse me, Boolean algebraic expressions, because it turns out that the exclusive or itself is not a low-level gate. We talked about how and is kind of like a series of switches. All the switches have to be down for a connection to be made. We talked about or being like parallel switches, where if any one of them is closed, we have a path. Exclusive OR doesn't have that kind of a configuration. We can't do something like that. Turns out that an exclusive OR is made up of ands, ors, and nots. So, but we're going to do this in this identities of Boolean algebra table just to kind of see the uniqueness that these logic operations give us. And then I'm going to make columns. I'm going to say with self, with inverse, with 1, and with 0. Okay? And so these are the different ways we can combine, you know, kind of like whenever anything added to 0, or anything ANDed with 0, or ORed with 0, or exclusive ORed with 0. And we're going to prove each one of these. Now, how do we prove things? We prove them with a truth table, because in Boolean algebra, it's very easy to enumerate all the possible combinations of inputs we could have to a circuit in order to see what the output would be. Now, for each one of these, I'm going to go ahead and I'm going to write down what the expression looks like. For example, when I say anding something with itself, that's like A and A. Or ORing something with itself, A or A. Or exclusive ORing something with itself, A exclusive ORed with A. All right? And in fact, let's go ahead and finish this table up. Being combined with an inverse, so A ANDed with A bar, A ORed with A bar, A exclusive ORed with A bar. And then with 1, A and 1, A OR 1, and A exclusive ORed with 1. And then in our last column, if we've got room here, A or 0, excuse me, A and 0, A or 0, and A exclusive ORed with 0. All right. Now, so what are we looking at? We're looking at a truth table. Let's just go ahead and make a truth table here. The values of A. How many possible values of A do we have? Well, 0 or 1. Just those two possible values, right? So, let's do the first one. How about A ANDed with A? Well, A ANDed with A is just 0 and 0, which is equal to 0. In the case of A is equal to 1, that's 1 and 1, that's equal to 1, right? Anything ANDed with itself, you've got 0 and 0 is equal to 0, 1 and 1 is equal to 1. Well, if you look at it, it looks like it just simply follows whatever A is equal to. That's what the output is. That's what the output of A and A is equal to. In fact, it's kind of like any number of A's ANDed together. That's going to be equal to A. So I could have A and A and A and A, and they'd still all simplify down to A. So Anything ANDed with itself is just equal to itself. Now, something that's important to notice here is that this doesn't just apply to just a signal A. It could be that I have B or C ANDed with